All right, hello everyone. So as Ali introduced, my name is Robert Good. I work for the Center for Water and Energy Efficiency with the Energy and Efficiency Institute at UC Davis. Today's conversation is a topic that's relatively close to me, and I'm going to try not to dive too much into the technical details and instead take you on a journey of the research path and let you in a little bit on the research opportunities and research subjects that SWE has in progress now around water demand management. So we'll go through the research question that we're trying to answer. For the benefit of those who are not necessarily partners with us at the Energy and Efficiency Institute, I'll talk a little bit about the water, energy, and Nexus, and then I'll go into 3 case studies of the research opportunities and research subjects that we're diving in around water demand management. So the research question is, how can we enable energy efficiency and load shifting to the benefit of California and the California energy grid through water demand management, specifically by looking at the residential, commercial, and irrigation sectors? So I want to give a little bit of an introduction that we primarily dedicate ourselves to addressing conceptual, technological, or policy barriers to improving measurement, monitoring, and management of statewide water and energy resources. And we understand that while energy load shifting and energy management, typically you think of that as a practice of installing potentially batteries or taking advantage of flexible assets or perhaps installing automation at commercial or industrial facilities. We look at water demand management as a form of a flexible asset. You can think of your local water supplier and water distribution organizations as principally being led by the water demand of their customers. And as a research organization, if we can publish work that results in water management, water load shifting, or water conservation, you can use that as a means to influence the energy demand of water supply. You can also use that as a means to modify the energy demand of the residential irrigation customers themselves directly. And I'll talk about that in the next couple of slides. So just to introduce the water energy nexus, typically in the water sector, we look at the entire life cycle of water in California as upstream or downstream of the customer's end use. In this case, upstream of an individual customer might include sourcing and extraction of your groundwater or source water, including treatment, distribution, pressurization, until eventually it reaches your home or your office for end use. Following end use, whether it's flushed down the toilet or it goes down your sink, that will be collected, that'll be treated, depending on the end use following treatment, whether that's going back to the source for following extraction, groundwater remediation, or it'll go through recycled water treatment for nearby or on-site reuse for more energy efficient and water efficient practices. So water customers are the driver of how water systems supply, source, and move water. Therefore, by changing water customers' activities, we know we can change the upstream water life cycle as well as the downstream life cycle. Wastewater treatment may not be necessary, and less water transportation or distribution may be necessary. Now, of course, looking statewide and understanding what the relationship between energy and water is important. So SWE has already investigated that question and has identified that the water life cycle in California can be broken into basins. And here we're seeing a breakdown of various regions in California with different energy intensities, which means how much energy was utilized either in delivery of that water or in utilization of that water after delivery. And the point that I want to get across on this page is that different regions of California do have different energy intensities. So you can start to understand that if your pursuit is water load shifting, then there will be certain regions that are more beneficial for water conservation or water load shifting than others in the pursuit of indirect energy savings or energy load shifting. Now, of course, you can take this one step further. Instead of looking at the California statewide scale, you can dive into one of those basins, dive one step further into your local water supplier, and start to understand how that water supplier operates, how much energy they're specifically inputting into your water in order to deliver it to you at quality and at a reasonable pace. So in this case, this is a diagram of the East Bay Municipal Utility District, which is within the Pacific Gas and Electric Service Territory. And we analyzed several of their pressure zones. And here in this diagram, you can see that some pressure zones are on the low energy intensity scale relative of that statewide figure. However, there are pressure zones that go up by a magnitude of 4 in terms of energy intensity. So what that tells me is, again, at this higher scale, or at this higher resolution scale, you can start to observe that certain neighborhoods, potentially specific customer classes or certain office areas, may be better candidates for water conservation and water load shifting in pursuit of energy conservation or energy load shifting. So right there is the first opportunity for a research question or a research project that we can pursue. And I'll talk about these in greater detail in the second half of my presentation. So the first opportunity is by building an even higher resolution energy intensity map for water delivery to help conservation and efficiency programs to target specific customers. And again, I will come back to this. Now, after you've targeted which customers are ideal for water conservation and water load shifting, we now want to start understanding the customers themselves, and we want to start getting into water demand management proper. So in this case, this is a figure that shows the profile or pattern of residential, irrigation, commercial, industrial, and so on, customer use patterns for water. So in this case, if you're looking at irrigation, you can see that typically in California, irrigation usage maximizes or has a peak around 4 or 5 a.m. with a daily minimum around 2 or 3 p.m., which makes sense if you observe your irrigation or your local golf courses. Similarly, you can see a pattern that starts to identify residential or your indoor water use. And here you start to see what makes sense of perhaps an early shower maximum in around 8 or 9 a.m. period, and a afternoon peak that seems to correlate with afternoon kitchen activities or after work showers. So we can take these water demands, and of course there's other qualities to take into account. Besides customer type, you may have season, depending on the hour of the day, clearly on these patterns, or even the weekend or weekday, which will clearly have different use patterns. So this presents another opportunity for us to investigate, which is if we understand the profile of customers, and we can use that to perform our research, what value and what impact would a customer themselves have if they knew in real time and high resolution their own water usage data? So in other words, if we streamed back to the user their own information in such a way that was comfortable, stimulating, and raised their awareness, would they result in a behavior change, whether that's reducing their water usage or simultaneously reducing their energy usage? And you'll see when we talk about this particular research topic, that does happen. So the last opportunity, I'm going to double dip on the same topic for the purposes of this presentation. What if you communicated directly with large water use customers? In this case, I'm going to target irrigation or golf course customers. And ask them to specifically shift the irrigation schedules forward or back by only an hour in order to reduce or modify the water use curve across the utility. Would that provide opportunities to the utility to better operate more efficiently, thereby reducing the embedded energy of the water shipped to the irrigation customer? So that's the third research topic. And now we're going to shift to the second half of the presentation where I focus on the individual projects or research opportunities themselves. So the first is targeting energy intensity values or an improved energy intensity map for water utilities. This is research led by one of our graduate student researchers, Richard Lee. The topic here is taking a hydraulic model or computer model of a water distribution system's network and operations. That includes things like their pipes, the locations of individual customers, the water consumption at that individual customer. You may have pump stations with flows, head loss, efficiency, and energy demand. And of course, you'll have tanks or storage that stores that water for later use in other hours. The simulation I'm showing here is utilizing a hydraulic model to perform a chlorine injection simulation. In this case, though, we're doing a unique twist in order to answer the research question. Instead of simulating an injection of chlorine and then seeing how that flows through the water system, we're utilizing an injection of energy in the water stream just upstream of the pump itself. This allows us to essentially inject embedded energy literally into the water supply, simulate the destination and consumption of that water to understand the life cycle of embedded energy at extremely high resolution. In this case, we're able to match the resolution of a hydraulic model, which with today's science is as high resolution as it gets for simulating and understanding the operations of urban water distribution systems. In this case, the simulation you're seeing starts at a blank slate of no chlorine or no embedded energy in the water system at all, and we're allowing the pump station to begin flowing. Now, this is not the only pump station in this model that I'm showing you. There's one over here, there's one down here as well. And so there's a couple of things that you as a water conservation program researcher or a program manager could take away from this type of model. One, intuitively, one pump station does not necessarily just share its water freely with the entire hydraulic system. In this case, you can see that the pump station prefers for the life cycle of its water to be consumed locally at nearby customers, which makes sense. But the thing that's important is you can start to understand that there are simply areas where that water from this pump station do not ever reach. And there's specific areas where intuitively you may have attributed the energy intensity of these customers to this pump station, but that's simply not what we observe in the simulation. This, again, empowers users to make better decisions in terms of targeting individual customers to understand how much energy they consume in utilizing their water. And you can start to attribute not only the amount of embedded energy that that customer resulted in, but the source of that embedded energy to help you target either customers, better pumps, higher efficiency pumps, or other conservation program alternatives. So here's an example of what a conservation program manager may choose to do with a map of this design. By understanding that certain customers do not receive almost any of their water from a selected pump that they're simulating in this map, they may decide whether or not energy load shifting is appropriate for them at that location, depending on the energy costs, maybe the rebate or incentive programs available to them. They can go through each of their pump stations to ask this question and begin to identify what the best opportunity for them is. And then lastly, this would help the program manager to perform water demand shifting using their program methods, whether that's a rebate, an incentive, or some of the other options we'll talk about, at these high energy intensity customers. So this is a very powerful tool that we're in the process of developing. Okay, the one downside I do want to mention about this opportunity is, or this research subject, is that it requires a significantly large amount of data to perform well. And so that requires potentially a very costly or time, it requires a great deal amount of time of researchers, in this case, a graduate student researcher, to perform this type of analyses. But it's of great benefit to water utilities to do so. The second opportunity or research topic I want to discuss is the spillover savings from raising awareness of water consumption to customers themselves. In this case, we're partnering with the East Bay Mud Municipal Utility District to perform a randomized control trial where we install high-resolution water meters at many customers throughout their utility district. Some of those customers receive regular messaging as all customers in East Bay Mud do. Some customers are now given up-to-date, high-resolution, real-time water use data. The question being, would those select customers make a different decision? Would they change their water consumption or their energy consumption? So here is an example of how the messaging would change for a customer who's receiving that high-resolution data. And then if the user dives into their web portal to see their individual usage, here you can see a customer can dive into long-term or short-term usage and start to really ask themselves and start to understand how they're using water and what that means for them. Additionally, while they're presented this information, they're also being given the opportunity to review other energy or water-saving upgrades for their homes. For example, they may be advertised for upgrading their dishwashers, washers and dryers, thermostats, or faucet aerators, and so on. The benefit to us is that this high-resolution data is not only going to East Bay Mud customers, it's also coming to UC Davis directly. We're using this information to analyze individuals and groups in extremely high detail that previously was never possible. And so in this case, we can observe the impact of a weekday versus a weekend on overall and individual customers in East Bay Mud territory. Of course, this is extremely powerful to researchers to allow them to piece out the impact of what this information what impact this information had on individual customers depending on which group they were in. So in this case, we're able to calculate constantly and in near real time the direct comparison between customers who did and did not have access to the high resolution data. And in this case, what we're finding is that there's about 4 to 6% absolute or overall savings in water use between the two customer groups just by informing them of their water use. Additionally, we're observing 1 to 3% spillover in savings in electricity use at no additional cost besides informing a user of their water use and advertising them the ability to upgrade their energy or water efficiency of their home. So this has been extremely successful. And while we're only 6 months into this pilot, I'm very excited for the publication in the following 6 months. Last opportunity I want to talk about very quickly is golf course irrigation scheduling. So in this case, we partnered with the Molten Miguel Water District in Southern California to research their reclaimed water distribution system to better understand opportunities for energy load shifting. So in this case, we utilized a hydraulic model again for this water distribution system. This particular model is about 2 orders of magnitude larger than the previous model I showed you. So in this case, we utilized the hydraulic model to research their water distribution or water patterns for individual customers and customer classes throughout their entire system, and in this case, the reclaimed water system. Of the reclaimed water system, the vast majority of their demand can be attributed to golf courses. And so this presents a really interesting opportunity in understanding golf course irrigation habits and how they can be changed using friendly communication and essentially a beneficial relationship between the water utility and the golf course to perform water demand shifting essentially via phone call. So here we can see that the original irrigation demand curves for golf courses in Molten Miguel's area has only been modified slightly to decrease the peak and disperse it over just a few hours around that peak period in order to enable more robust management of the water system. Now, what do I mean by that? So this water utility is extremely complex. They have many pump stations and water sources. And if you have the ability to change water customer demand, could you then reevaluate your operations? And so we did that twice. We reevaluated the operations for the highest possible efficiency without load shifting of the water customer's demand and with load shifting the water customer's demand. And here's what we found, that by reevaluating the controls of the system without water shifting, there are certainly opportunities for improvement to the water system's operations, whether that's the amount of water they pump or their overall energy consumption. However, I want to emphasize, by shifting water demand of just the golf courses by just a few hours back and forth, we're able to increase the capacity for improvement to the system's operations significantly. This is a low-cost implementation for Molten Miguel to have a positive relationship with their golf courses, shift the golf courses' irrigation schedules forward or back, which is a relationship they are already able to have. It just becomes a question of, once they do that, perform the reevaluation, these benefits are yours. Now, comparing that performance and that type of project, reevaluating your entire controls from your water system seems like a costly maneuver. But what we're finding is that it pays for itself because of the efficiency gain. And of course, if you compare this to other efficiency opportunities for reducing greenhouse gas emissions, what we're finding is that this project, performing water demand shifting and then overall reevaluating your controls, is a very, very competitive solution versus other opportunities, including, I want to point out, overall water use efficiency. So with that said, I want to thank you for listening to my presentation and to the 3 research topics that our center is currently investigating. I hope it was interesting to you, and if you have any questions, please put them into the chat log now, and I'll await the first round of questions. Thank you.
You here for a minute so you can ask a question.
Thank you. Excellent presentation, very exciting. My question is, you're performing research now. Are you looking for new partners in any of these research areas, or do you have research projects in the pipeline where, again, you might be looking for partners?
That's always a great question. That is always the case. So for the 3 projects I outlined here, the last 2 are currently in pilot. So as far as looking for additional partners there, the partners we will be seeking are expansion opportunities for those existing research projects. So I'll give the example of the Molten Miguel project. If we were to find a energy or water supply utility that was interested in that research and interested in expanding that research to their territory, 100% that would be a conversation that we can have. For the pre and post socioeconomic study for East Bay Mud, this is our 2nd time performing a similar pilot, once with Burbank, the 2nd time now with East Bay Mud, this time just of being twice as large of scope. So if we were going to partner for a similar project with that, I would emphasize it would have to have a unique twist, simply because duplicating research, beyond obviously increasing the scope, you want to start investigating new avenues. So if there's a unique opportunity for how your customers can be communicated with, that's something of interest to us. Or perhaps for the first project, an understanding high resolution energy intensity maps, that simply becomes a question of the availability of data. Not every water utility necessarily has data readily available for this type of project. So we're always looking for water energy suppliers with enough data available that we could start performing analytical analyses on their water system or their energy supply systems. Did you have anything in mind?
Several things, but I will follow up with you after the webinar. But this is very exciting, the work that you're doing, and I'm happy to learn about it.
Great.
Perfect.
Thanks,
Thank
Chris.
you very much for your question.
I'll get started. Good afternoon. My name is Nelson Dichter. I'm a senior research and development engineer at the UC Davis Western Cooling Efficiency Center. And I'm here today to talk to you about my research analyzing NOx emissions from hybrid heating technologies in California. My research primarily compared the NOx emissions of different heating systems in residential buildings. Nitrogen oxides, or NOx, are a group of pollutants that are produced from a reaction between atmospheric nitrogen and oxygen during the combustion of fossil fuels, such as the combustion of natural gas in furnaces to heat buildings. NOx are harmful and toxic greenhouse gases that contribute to acid rain, global warming, and respiratory issues like asthma. The 2 most common types of HVAC systems used in residential buildings in California are a natural gas furnace paired with an air conditioner and an electric heat pump. An electric heat pump must be sized for either the heating load or the cooling load of the building, whichever is larger. Since most buildings do not have a balanced heating and cooling load, sizing an electric heat pump results in oversizing the capacity in one mode or the other. In residential buildings in many climate zones, The heating load is significantly larger than the cooling load. An alternative to these systems is a hybrid heating system, which contains a heat pump paired with a low NOx gas furnace. In a hybrid system, the heat pump is used as the primary source of heat and the furnace serves as the auxiliary source of heat. The heat pump operates during mild temperatures. As outdoor air temperature drops and the heat pump can no longer meet the heating load of the building, the system turns off and the system turns off the heat pump and switches to the natural gas furnace. By reducing the number of hours in the year that the furnace must operate, the hybrid heating system reduces the annual NOx emissions of the furnace. Since the furnace can be sized to meet the heating load of the building during the coldest hours of the year, the heat pump can be sized based on the cooling load instead of the heating load, reducing the required system capacity. Whole building annual energy simulations were conducted using Energy Plus to estimate the annual NOx emissions from low NOx furnaces, which emit 40 nanograms per joule of heat, ultra low NOx furnaces, which emit 14 nanograms per joule of heat, and hybrid heating systems in California residential buildings. 2 levels of insulation were simulated, one that is representative of new construction with R13 in the walls and R19 in the ceiling, and one that is representative of existing construction with R8 in the walls and R11 in the ceiling. Weather was simulated in each climate zone using typical meteorological year weather data. The population distribution reported in the 2010 California census was divided among the California climate zones, resulting in the population distribution shown in the table. The baseline single-family residential building was modeled with a single-speed CR14 air conditioner and a low NOx furnace. The hybrid heating system was modeled as a single-speed heat pump and a low NOx furnace. The heat pump has CR14 as well and a heating seasonal performance factor of 8.2. Generic performance curves were used to model each HVAC system. This figure here shows the operation of the heat pump and furnace in the hybrid heating system using the outdoor air control strategy from January 31st to February 1st in California Climate Zone 16. The building was insulated to represent new construction and the sizing factor for the heat pump was 1.7. For these examples, a cold climate zone and a large sizing factor was selected to determine the difference between the behavior of the 2 control strategies. In warmer climate zones and with smaller sizing factors, the behavior of the 2 control strategies is less distinct. Whenever the outdoor air temperature drops below 32 degrees Fahrenheit, the heat pump is turned off and the system switches to furnace operation. You can see that by following the red line here is the furnace operation. So when the yellow line is the switchover temperature, when the outdoor dry bulb temperature drops below that switchover temperature, the furnace kicks on and maintains the heat in the building until the outdoor air temperature rises above the switchover temperature, at which point the electric heat pump, which is shown in the green line here, kicks on and takes over the heating of the building. This figure shows the operation of the heat pump and the furnace in the hybrid heating system using the indoor air control strategy. All other simulation parameters were the same as before. Using the indoor air control strategy, the hybrid heating system relied more heavily on the heat pump and only switched to furnace operation when the system was unable to satisfy the heating load of the building. So you can see that here, that even though the temperature was below what we had said before was a switchover temperature, the gas furnace didn't kick on until the heating system was no longer able to maintain the indoor air temperature. And then even over here where the outdoor air temperature again dropped below the switchover temperature, the heat pump was adequate to maintain the indoor air temperature, so it just continued to operate in heat pump mode. These results show how the emissions reductions achieved with the hybrid heating system compares to the 65% reductions achieved with an ultra-low NOx furnace. Using the indoor air control strategy, the hybrid heating system was able to reduce annual NOx emissions by more than ultra-low NOx furnace in all California climate zones. Using the outdoor air control strategy, the hybrid heating system was able to reduce annual NOx emissions by more than ultra-low NOx furnace in all climate zones except California climate zone 16, which is the coldest climate zone in California. It's Tahoe and other high altitude areas like that. The better insulated building had a smaller thermal load, resulting in fewer annual heater operating hours and NOx emissions. However, the building insulation had little effect on the percentage of the NOx emissions reductions when compared to the hybrid heating system to the low NOx furnace. So based on these results, essentially we concluded that the building construction only affects the magnitude of the reduction in the NOx emissions, but doesn't really have an impact on percent difference. So moving forward, we stuck with new construction building parameters for simulations. These results show how the sizing factor affects the annual NOx emissions reductions in each California climate zone. As the sizing factor increased, the annual NOx emissions reductions also increased. With a larger heat pump, the hybrid heating system satisfied more of the heating load with the heat pump instead of the furnace, resulting in less natural gas use and consequently reduced annual NOx emissions. When the sizing factor was 1.3 or greater, the hybrid heating system using the indoor air control strategy was able to achieve larger NOx emissions than an ultra-low NOx furnace in all California climate zones. However, due to the cold winters in California climate zone 16, the hybrid heating system operated at ambient temperature lower than the switchover temperature, which is 32 degrees F, approximately 36% of the time. As a result, in this climate zone, the outdoor air control strategy achieved significantly less NOx emissions reductions than the indoor air control strategy, regardless of the heat pump sizing factor. An additional benefit of hybrid heating systems is a reduction in CO2 emissions. Although ultra-low NOx furnaces reduce NOx emissions when compared to a low NOx furnace, they still burn the same amount of natural gas to provide a given amount of heat. Since CO2 emissions are a direct consequence of burning natural gas, ultra-low NOx furnaces emit the same amount of CO2 as the low NOx furnaces that they are replacing. While CO2 emissions are also embedded in the electricity that powers electric heat pumps, hybrid heating systems can significantly reduce CO2 emissions when compared to natural gas furnaces due to the efficiency of the electric heat pump and the large amount of renewables on the California grid, which, if current trends continue, will increase in the future. In this table, the population distribution in California was used to weight the simulation results. In California, the hybrid heating system, when compared to a low NOx furnace, resulted in an annual NOx emission reduction of more than 95% on average for all control strategies and sizing factors simulated. The average CO2 emission reduction of the hybrid heating system when compared to a low NOx furnace was between 67 and 69%. And those are essentially the takeaway results from this particular study. And that is what I have for that paper. Does anybody have any questions?
Great. Thanks, Nelson. Yeah, if you have any questions, please send us a note. I see one here from Greg, so let me unmute you, Greg. There you go. All right, Greg.
Hi, Nelson. I had two quick questions, hopefully. The first was what role you see these hybrid heating systems playing given the trend to start banning natural gas in buildings in California?
Right. As a retrofit option, essentially, because right now there's a lot of legislation going in that's trying to push the ultra-low NOx furnaces for buildings that are set up for a gas furnace and are not set up for a electric heat pump. So it's kind of a bridge technology to kind of get us from as far off of natural gas furnaces as we can. Because the idea is that since you can use a smaller heat pump, you wouldn't need to upgrade the electrical service for an air conditioner that's already in place if you are doing a retrofit.
Sure. And then my second, oh, go ahead.
I was just thinking it allows you to achieve most of the benefits of electrification without having to do with all the extra cost of upgrading to a full electric system on a building that was designed to be heated by a natural gas furnace.
That makes sense. And then I understand, or from your presentation, you said that you ran the simulations with a 1 degree Fahrenheit threshold of like if the electric heat pump wasn't able to meet the heating demand, then the natural gas would kick on.
Right.
Did you test at all other scenarios with kind of a wider threshold? It seems like that's maybe a little bit tight and people might not even notice at a 2 or 3 degree.
Yeah, we did. It didn't have a huge impact on the results, but it's also, I was trying to be as realistic to the way that the thermostats actually behave in these systems.
Okay.
So they generally, if they're not able to maintain set point within a degree, they usually will kick on the natural gas furnace, and they don't necessarily wait for the temperature to drop. They kind of, every manufacturer has their own algorithm for it, but they look for like rate changes, and if it looks like the temperature inside the building is dropping, even though the heat pump is on, they'll usually switch over. So I was just trying to like capture the actual performance. If you were to widen that band, it does actually improve the NOx emissions reductions, right? Because you'll be using the heat pump more than you would without. Another thing to note is that the outdoor air control strategy is not a common control strategy. It's out of the box. The systems usually just rely on the indoor thermostat temperature. In order to do the outdoor control strategy, you actually have to have the contractor install an extra temperature sensor that goes outside. So it's an extra cost there. And the only real reason that people use that one is because they're able to save some money, because the efficiency of a heat pump will drop as the temperature goes down. So when it goes, say, below 32 degrees Fahrenheit, it's going to cost you more money in electricity to heat the house than it would to run the natural gas furnace, or significantly more money. So they tend to switch over there. So it's a money saving effort. And I simulated that one largely because if people are considering these technologies for regulation, it's good to keep that in mind and to stipulate how the system's supposed to be controlled. Because, I mean, a contractor could install a hybrid heating system with a switchover temperature of, say, 40 degrees Fahrenheit, in which case you, in most climate zones, would still be doing better than ultra low NOx furnace, but you're not going to achieve nearly the same level of emissions reductions that you would with that operating scheme.
Okay, thank you.
All right, any other questions for Nelson or for Robert? They're both on the line. Nelson, are there any next steps in this research area? Or is this kind of,
No, so essentially, so the focus moving forward is going to be more on CO2, and we're kind of doing, just now I'm getting started on a national study that will be looking at the impact across the United States and really taking into account the asset makeup of different utility grids, because every grid has different marginal emissions rates and base emissions rates, and so kind of to take that into account, and the time of use will also be accounted for in that project.
Sounds great. Well, we had rapid speakers, speedy speakers this week.
Yeah,
and,
sorry, I try to slow myself down, but it's...
No, it was great. Usually I have the opposite problem, which is cutting people off. So you definitely win the prize for sticking to your time frame. Well, thank you everyone for joining us. We hope you can join us next week. We'll have 2 additional interesting speakers. One I know is on ground source heat pumps, and the other is still a mystery. So we will find out and let you know on Monday what our speakers will be talking about. Have a great weekend, and we look forward to connecting with you again. Take care, everybody. Thanks, Robert and Nelson.
Thanks, everyone.